Well, good morning, everyone. Welcome back for today's live Zoom session. It's good having so many of you signed on live for this. Do remember, if at all you experience connectivity issues, I am recording this session. It will be posted to YouTube with a link on D2L. But let's jump right in and start working on some examples. So we're still working with hypothesis testing, and we are looking at testing hypotheses about a population mean. So there's some null hypothesis making a statement about what we believe the population mean to be. We then take our evidence in the sample and we assess whether our sample evidence is consistent with the null hypothesis or not. And first half of the week, the way we did that was by calculating a test statistic and then determining if the test statistic was inside a rejection region or not. Now, the first examples we're working on today, we're still in the same scenario as before. So we're looking at a couple of examples here where we assume that we have a population that follows a normal distribution and that the population variance is known. And later on today, we will expand on this a little bit and look at other scenarios. But for now, that's what we're restricting our attention to. And so these first two examples, the setup is going to look very familiar because it's similar to problems we worked on Tuesday. But the way we want to approach them today is by looking at calculating a p-value as opposed to a rejection region. So there are a couple of formulas that you can just plug and play to get your p-value. But I'll try and, in these examples today, again, talk you through the logic behind where the p-value comes from. So let's look at this first example. It's the same one we had with the fire sprinkler system. So in this example, we know that our null hypothesis is that these systems on average activate at 130 degrees. And we want to test the truth of this hypothesis. Our alternative is not stated in any specific direction. It's not saying, oh, we believe that they activate at a higher temperature, or we believe they activate at a lower temperature, which would introduce direction. It just says we want to test the truth of this hypothesis, which means we have a very generic alternative contradicting the null completely, saying mu is not equal to 130. Now, the evidence that we collect in our sample, we have 20 observations. In the sample, we observe an average activation time of activation temperature of 131.08 degrees. We also know that this is coming from a population with a standard deviation of 1.5 degrees. So the test statistic calculation is exactly the same as before. We've done this for this specific example, x bar minus mu naught over sigma over square root of n. If I plug in all of these values, you can go and check the calculation, but we get a value of 3.22. This is what we need to calculate our p-value. P-value means we're referring to our bell curve, our standard normal bell curve, and in the case where we have a two-sided alternative, the p-value is the area corresponding to the bell curve, both, if you look at the observed value, we take the positive and the negative of that value, and what we want to find is the area in the tails of the distribution. Two-sided or generic alternative means we want the area in both tails. But the calculation of that is fairly simple. there is in fact just a formula that you can write down. The formula says it's 2 times the normal CDF at negative the absolute value of Z observed, which in this case means it's 2 times the normal CDF at negative 3.22. So what you're going to do here is evaluate your normal CDF. Lower bound will be negative infinity, upper bound will be negative 3.22, and that you are going to multiply by 2. So if you go and do this calculation on your TI-84 or your Inspire, for that normal CDF, you're going to get, to like 5 decimals, 0.00064. Multiply that by 2, and if I round at that point to 3 decimals, I get a p-value of roughly 0.001. Now, the p-value, determining what that says about your null hypothesis or not, is done by comparing it to the level of significance or to the alpha value of the test. So we want to compare the p-value to the alpha value. And what we have in this instance is a p-value of 0.001. If we compare that to the stated alpha in this case, alpha is 0.05, the p-value is less than alpha. Small p-value, I said in the recorded lecture from yesterday, means small probability that the null hypothesis is true. So if we're associating a small probability or a small chance of the null hypothesis being true, that means we are going to reject the null hypothesis. Right, and what does it mean if we reject the null hypothesis? You always want to provide an interpretation here. If we reject the null hypothesis in this instance, that means we are saying it is, based on the sample that we've observed, it is unlikely that these fire extinguisher systems have an activation temperature on average of 130 degrees. We are rejecting the idea that it's 130. Our hypothesis testing procedure is telling us that is an unlikely value because the sample evidence is not consistent with that. I'll pause here for a few seconds in case anyone has a question. You're welcome to hold down spacebar and ask, or there is a chat feature. You can type your question in chat as well. Okay, let's move on to our next example. If something pops up in chat, I'll happily look at that and answer. But I think we have another example very similar here, so it'll illustrate the p-value idea one more time. Another example that should look familiar, because we're still, we had a very similar problem on Tuesday, looking at light bulbs and what the average lifetime of a specific kind of light bulb is. Now, in this instance, our null hypothesis said the average lifetime is 750 hours. And we design an experiment to determine whether this is true or whether the actual lifetime is lower than the stated value. So in this problem, we are given a direction for the alternative. The alternative is mu is below the prior value believed to be true. Mu is less than 750. Now, if we look at the data that we've collected, we have a sample of size 50. In our sample, we observed an average lifetime of 738.4 hours. We assume that the population is normal and that it has a known variance of 1600 hours squared. And we want to go and calculate a p-value and then reach a conclusion at a level of 1%, or alpha equal to 0.01. Now for this, again, we want to start off by calculating our observed test statistic. And since we have normality and we have a known variance, we're calculating a z-statistic, and we know we can compare it to a normal reference distribution. So it'll be the sample average minus the value under the null hypothesis divided by the standard deviation, which in this case is square root of 1600, divided by square root of the sample size. And this you will find is 2.051. Now, when we calculate our p-value, the fact that our alternative has a specific direction affects how our p-value is defined. If our alternative is mu less than, that means we're only going to be concerned with the area below the observed z-value. So our observed z-value is roughly -2. And so in this instance, we're only concerned with knowing what the area is to the left of that value. Again, alternative says mu is below 750, so we want to know the area below the observed z-value. And the formula you can use here for calculating that is simply taking the normal CDF at the observed z-value. It's only in the two-sided case where you have to worry about taking absolute value, considering both the positive and the negative. In this instance, we're purely taking the observed z-value as is, and it just happens to be negative in this instance. So you're going to evaluate your normal CDF at -2.051. So if you take your calculator, you evaluate normal CDF, lower bound of -infinity, upper bound of -2.051. That will give you a p-value of roughly 0.02. How do we now reach a conclusion? Well, we have to compare the p-value to our alpha level. In this case, our p-value of 0.02, if we compare it to the alpha, which in this instance is 0.01, our p-value is greater than alpha. So large p-value, informally that tells you large probability that the null hypothesis is true. This is always a relative comparison. It's small if it's below alpha, it's large if it's above alpha. So in this case, p-value is above alpha, which means we do not reject the null hypothesis. Again, you have to state a final conclusion in the context of the problem. If we do not reject the null hypothesis, what that tells us here is we do not have any evidence that suggests the null hypothesis is false. In other words, no evidence to suggest light bulbs do not have an average lifetime of 750 hours. So without collecting any more data, we will assume that the null hypothesis is true. I think to wrap up these two examples, it is always important to remember, though, that whichever conclusion you're reaching, it is possible that you're making either a type 1 or a type 2 error. Now, in practice, you're never going to know whether that is happening. You can only know which conclusion you reach using the p-value. But if you reject the null hypothesis, you could certainly be making a type 1 error. But that is controlled by alpha. right? Your alpha level is the same as the probability of a type 1 error. In this instance, where we are not rejecting the null hypothesis, you could be making a type 2 error. And so this is maybe where, in practice, someone would sit down and do a separate calculation saying, oh, hypothetically, if the value were below 750, let's say maybe it was 730, how likely would it be that we're making a type 2 error? So that would be a separate calculation, but it would be a worthwhile one to do in practice to try and quantify whether you are at risk of making a type 2 error here. So again, I'll just leave a few seconds in case someone has a question, and then we'll move on to the next example. I also hope everyone has their beverage of choice. I am still on coffee for the morning, probably only my 5th cup. So no judgment, please. And I will not judge any of you regardless of what you're drinking and what time zone you're in. Okay, now our next examples take us into the other 2 scenarios that were introduced in yesterday's recorded lecture. So at this point, we want to start paying attention to a few different pieces of information. Firstly, you want to see in the problem setup whether normal distribution is an assumption that's being made. Secondly, you want to check whether the variance is known or not if you have a normal distribution. And finally, you also want to check if you do not have normality, if your sample size is large. Because even when you don't have normality, if your sample size is large, you will still be able to do an approximate calculation. Now, in this problem, we're looking at the percentage of, oh gosh, I think there was silicon dioxide, but I don't remember. Percentage of some compound in cement is known to be 5.5. We want to test whether this is the case for a specific production facility, and we want to use a 2-sided alternative. We have a sample size of 62. Our observed sample has a mean of 5.36, and our standard deviation for the sample is 0.281. Now here, we're not given any information about normality, right? Normality is not stated, but our sample size is at least 30. Which means we can do an approximate calculation still using the normal distribution. Okay, so the calculations will proceed exactly as we did before, still using the z-observed statistic and normal CDF as a reference, but what we'll remember at the end of the day is what we're calculating will only be an approximation and not a true exact value. But that being said, let's look at the different parts of this problem. So even though it's not asked, I am going to state here the null and the alternative hypothesis. Our null hypothesis is that at this facility, we still have 5.5% levels of the compound in the cement being manufactured. And our alternative is that the value is different from 5.5%. Right. The reason the null and the alternative hypotheses are important is they determine both how you calculate your rejection region and how you calculate your p-value. So in this instance, when we now get asked for a rejection region, we know because we're dealing with a two-sided alternative, our rejection region is defined to be any time the absolute value of z observed is greater than or equal to z of alpha over 2. Now, this is an approximate rejection region. It's what we would use to reach a conclusion, but it's not an exact because we don't know what the underlying distribution is exactly. So that being said, our alpha in this case is 0.01. Because it's two-sided, we're working with alpha over 2. And so we want to find the z value of area to the right, 0.005, which means you're going to use your inverse normal function on the calculator. The area to the left of that value is 0.995. And if your calculator is asking for reference mu and sigma values, those are 0 and 1. So if you go and evaluate this, you will get a value of 2.576. So if you were to do a test here using a rejection region, you would reject the null hypothesis if the absolute value of z observed was greater than or equal to 2.576. Now, second part of the problem is asking us to calculate the p-value for the test. P-value requires that we first go and calculate the test statistics. So we need to calculate z observed. In this case, the formula would be x bar minus mu naught divided by s over square root of n. Again, S, because that's the information we've been given. We don't know the population standard deviation. We do know it for the sample. And that doesn't really affect anything here because our sample size is large enough that the normal approximation would hold either way. So plug in the observed values. And we get a value of 3.923. Now, before I do go on to my p-value calculation, you can immediately now check what conclusion you would reach using the rejection region method. That observed z value, if I take absolute value of it, 3.923 is much larger than the 2.576 threshold. So this is inside the rejection region. So using a rejection region, we would reject the null hypothesis. Now, p-value, our alternative here is two-sided. So we want to calculate the total area both to the left and to the right of the negative and the positive z observed statistic. Again, that's as easy as saying we're going to take 2 times the normal CDF just at the negative z observed value, negative of the absolute value of z observed, which in this case ends up being the same value. So if you go and do this on your calculator, what you will find is that this is roughly 0.0001. So our p-value, if we compare that to our alpha, in this case of 0.01, the p-value is below alpha. Small p-value, small likelihood that the null hypothesis is true, and so we, in this case, reject our null hypothesis. So whether you're basing it on the rejection region or whether you're basing it on the p-value, you will always reach the same conclusion. And I often write exam problems where you have the choice. You can go either the p-value route or you can go the rejection region route. You should be able to do both. You should be comfortable doing both, but many times I will give you the option. I'm not going to promise that every single problem will be that way, but worst case scenario, I will say this. If you get an exam problem and it's trying to force you into a p-value and all you can do is rejection region, solve it using the rejection region because you will still get partial credit doing it that way. Now, this problem does have a part C, which has to do with estimating the type 2 error. I'm going to skip over that for this live session, but I will insert a page in this document just showing you that calculation. We did a few of those on Tuesday. I don't want to get stuck on that now because it's just tedious, long, lots of writing example. And we did it on Tuesday, something similar on Tuesday. So I'll insert that. Please review that in the notes afterwards. Okay, let's look at our next example. So in this instance, we are looking at how much water gets consumed in single-family homes. We are told that water consumption in single-family homes follows a normal distribution, and in the US is known to have a mean of 20 gallons. We want to test whether this national number, this reference number of 20 gallons, also holds in Fort Worth. And so we are going to take a sample of 17 homes, and we're going to monitor their water usage. The City Council believes that Fort Worth is actually below the national average. So this immediately gives us our hypotheses right. Our null hypothesis is that the mean in Fort Worth is 20, but the City Council believes that in Fort Worth it's below 20. People in Fort Worth are very conservation minded and they're not using too much water. Now, what do we observe in this sample? For our sample size of 17, we observe an average of 18.38 gallons and a sample variance of 9.14. So we have normality, but we don't know what the population variance is. These two facts, normality and unknown variance, means we have to use a different test. We're no longer going to calculate a Z observed value. We're going to use a T test and calculate T observed. So remember, the moment you have normality, but the population variance is unknown, you're switching over to a T test as opposed to a Z test. Implementation is going to look very similar. In fact, what I now call T observed, it's still X bar minus mu naught over S over square root of N. So the formula doesn't really change from Z observed. I can plug in my numbers here. Observed average is 18.38. Average under the null hypothesis is 20. My standard deviation is the square root of 9.14. And I have a sample size of 17. So if I plug all of this into my calculator, I get a T observed value of negative 2.209. Now, we're trying to get a p-value here, and this is the other instance where you have to be careful, because we now are no longer using a normal distribution as a reference. We're using a T distribution with n-1 degrees of freedom. So in this case, a T distribution with 16 degrees of freedom is our reference. Now, our alternative determines how we calculate our p-value. Alternative says mu is below a certain level, which means we want the area below our observed test statistic. We want to determine here how much area is below this value of negative 2.209. But we have to do it now using the t-distribution CDF. So our p-value is going to be the t-CDF, lower bound negative infinity, upper bound negative 2.209, and degrees of freedom, sample size minus 1, so in this case 16. And if you plug all of that into your calculator, you will get a p-value of 0.021. Ultimately, to reach a conclusion, you have to compare that p-value of 0.021 to your alpha level. And this problem, if you look at how it's formulated, we're working with an alpha of 5%, so an alpha of 0.05. So our p-value is less than alpha, which means we reject the null hypothesis. What does that tell us about Fort Worth? Well, it means the sample is not consistent with the null hypothesis. This is actually what the City Council is hoping to find. The sample is showing us there is evidence that Fort Worth homes use less water, right? The average consumption is 18.38 gallons, and because we're rejecting the null hypothesis is the most plausible value. So reject the null hypothesis. Yes, there is evidence that single family homes in Fort Worth use less water than the national average in the US. So while I scroll to the next example, again, if anyone has a question, you're welcome to take a minute now and ask that. Okay, here's our last example for today. We are looking at how much cranberry sauce homes use in Texas. And the evidence or the information we're being given says that the typical family in Texas consumes 15.5 ounces of cranberry sauce during Thanksgiving. We want to test whether the true average in the DFW Metroplex is equal to the statewide average. And if you read the whole problem, you'll see that it doesn't say anything about whether we believe it's below or above the national average or the statewide average if we just look at DFW. So our alternative here is going to be a generic two-sided. If you're not being given a specific directional prompt, less than, greater than, then your alternative is two-sided. The data that we collect for a sample of size 12, we find average consumption of 16.8 ounces and a sample standard deviation of 2.88 ounces. And we have a normal distribution as a reasonable assumption here. That being said, we have normality, but our population variance is unknown. Normality and unknown variance means we're going to use a t-test. So our t-observed statistic is x bar minus mu naught over S divided by square root of n. So 16.8 minus 15.5 over 2.88 divided by square root of 12, and that gives us a t-observed value of 1.564. For the p-value, because our alternative is two-sided, we want to determine both the area to the left of the negative of our t observed and the area to the right of the positive value. So the shaded region here that defines our p-value. So the way you would do this is 2 times TCDF. Because of the symmetry of the t-distribution, which it has in common with the normal, you only have to calculate it on one side of the curve and then multiply by 2. So I'm calculating the shaded area on the left, which means lower bound negative infinity, upper bound the negative 1.564. And remember, degrees of freedom will be sample size minus 1, so 11 degrees of freedom here. What does this give me? 2 times 0.073, which means my p-value is 0.146. So I want to compare this p-value of 0.146 to my alpha value, and alpha in this case was 1%. So my p-value is larger than alpha. Large p-value means I am not rejecting my null hypothesis. So I am not finding any evidence in my sample that suggests homes in DFW or families in DFW use either more or less cranberry sauce than people in the US on average, right? My sample is consistent with the null hypothesis, so my best conclusion is that homes in DFW also consume on average 15.5 ounces of cranberry sauce. So to wrap up for today, remember you have your first online homework submission that's due tomorrow, so you still have a day to work on that. I will get up the next homework assignment today, and the one I post today will be due on Tuesday of next week. And then I'm going to wrap up recording here, but I will stay online for a few more minutes in case anyone has questions. So thank you everyone for tuning in, and just hang around if you have questions. I'll be happy to answer those.